So this is the simple example of AC circuit. As already we have seen the definition, so we have circuit consisting of a resistor and a alternating current source or alternating voltage source. This is a regular symbol for alternating voltage source. Now the EMF of this source or applied by this source. So just check this here. In the regular DC source or regular battery or a cell, the EMF applied by the cell is denoted as E, curved capital E. Actually it's the same symbol is actually used even here also. The equation already we have seen here in the rough column as a revision of the previous topic, AC generator. Now so just check the heading here. A resistor applied with an alternating voltage. That means an alternating voltage is applied across the resistor. So that alternating voltage or voltage here means EMF. It also means potential difference. So the EMF of a cell is E means EMF by definition. We have seen 5 definitions for EMF in the lesson current electricity. In the functioning of a cell or a battery, we have seen firstly that first definition, basic definition of EMF of a cell. So later in potentiometer, during potentiometer topic, we have seen the other 4 definitions also. So EMF of a cell is really the maximum potential difference applied by the cell across any resistor or across any device. So EMF is E means that's the potential difference actually applied across the resistor roughly. That's the meaning of EMF. Based on the definition of EMF, we can say this. It's not exactly. Why it is not exact also we have seen earlier. But roughly EMF is nothing but the potential difference roughly applied across the resistor by the cell. So this is the EMF of this source means it is the potential difference applied by the source across the resistor. So this EMF, this potential difference is nothing but alternating potential difference or alternating voltage or alternating EMF. So now the important thing is the current sent by this source through the resistor. It is denoted by the same regular symbol I. But now the important thing is there is a fixed direction for current in the DC source, but there is no fixed direction. That's why in the circuit the direction of current is actually not shown. Even this direction also upwards also should not be shown exactly speaking. So just it's simply shown as I, but it will be a little inconvenient because if direction current means or some direction should be shown actually. That's why actually direction is shown a little outside the circuit actually. We're just assuming that initially this for short time interval current is flowing in the clockwise direction this way. But in the next time interval current direction will be changing, so it will be flowing anti-clockwise. That means the arrow should be downwards here in this part of the circuit. So that's the thing here. So now the that's the simple circuit here, simple alternating current circuit. Now the important thing is from the AC generator derivation we have seen that the alternating EMF applied by the source across the resistor or alternating potential difference applied by the source across the resistor or the alternating voltage applied by the source across the resistor basically is given by this equation 1 of the rough column. So that equation, so we can just take it directly. So the EMF applied by the source, it's a sinusoidal function of time given by E is equal to E naught sine omega t. So here also this equation is taken as a result 1. So though we did not derive it here, that's actually the starting step of this particular derivation taken as result 1. It's taken as equation 1. It's not a result actually. Here we are using that result we obtained in the previous lesson or previous topic belonging to the previous lesson. So that's the alternating EMF, and where E naught is what here? The peak EMF or peak value, maximum value of the EMF. So that's the equation here. Now the important thing now is the direction of this EMF, initially assuming that it's clockwise. So taking this terminal left term, so current is sent in the clockwise direction by the source. Means always current flows from the positive terminal of the source to the negative terminal. So that means this terminal, left terminal should be positive terminal. So again the positive and negative terminal should not be shown here because the directions, the signs, positive nature and negative nature, they will be alternately changing in continuously at regular time intervals. So left is positive, right is negative, always fixed for a regular source like a battery DC source. But here its directions will be changing, the polarities will be changing. So it should not be shown. But for convenience to show that current is flowing clockwise means this terminal definitely should be, because it's sending current in the clockwise direction, this terminal should be positive and this terminal should be negative. So I'll just indicate the positive terminal here and negative terminal here. So that so I just remove this one. So but that's the important thing is it should not be shown exactly. So I'm just putting this in brackets. So whatever things we are putting in brackets, actually they don't belong to the circuit. They should not be drawn in the examination. So very important thing is scientific derivation is the most powerful thing in science and technology, because it's directly based on fundamental laws and definitions, or the direct results obtained from the fundamental laws. So Faraday's law is almost like a fundamental law. It's almost like a fundamental law of this lesson. So directly based on Faraday's law, in one or one and a half steps we get this particular equation. That's why this is also almost close to a fundamental law. So very powerful equation, this equation. Very important throughout this particular lesson, which we got in the previous lesson. AC generator, construction, working and theory. So whatever things actually we are just assuming, so they have to be kept in brackets. So even this current also should be kept in brackets. So because if I keep it that in brackets now, the figure already has become congested, so I don't want to keep this. In the end I'll just put this in brackets using some other a different color, so that the actual diagram will not be disturbed. So this is like positive terminal. Now for a short time interval, current is flowing clockwise. Left terminal is the positive, right terminal of the source is the negative terminal. So that's the thing here. So now the aim of the derivation is we have to get an expression for the alternating current. That means an expression for I is required when it is applied with the alternating voltage. So this alternating voltage, actually regular symbol for voltage or potential difference is V. So in place of that V here, what we are using is the EMF E is we are using. But it can be now the exact relation between potential voltage and EMF will be getting immediately in the next step itself. Actually both of them will be one and the same. What is the reason means the reason immediately in the next step will be same. So now we require an equation for the alternating current in terms of the voltage, or the, at least now for the present, in terms of the EMF. That is what is the aim of the derivation. But that already we got this here. If the alternating EMF is E, then from this equation only we got the alternating current. So but how did we get this result from this? Directly using Ohm's law. Directly using Ohm's law we got this particular result. In any resistor, if the voltage is known, then current is given by V by R using Ohm's law. So what was the Ohm's law? V is equal to IR, or I is equal to V by R. Based on that equation, in one step we got this particular equation actually. I is equal to I naught sin omega. I try to remember this particular derivation. How we got this equation means directly applying Ohm's law we got this equation from this. Then what is the aim of this derivation presently? What is the aim of this particular topic? This particular topic also means the same thing. We have to again get from EMF, we have to get the current. But the difference here is we'll be using slightly different symbols here. Not just the slightly different symbols, even method also will be slightly different. Here we have used Ohm's law, but Ohm's law is a very simple law applicable only for very simple circuits containing only resistors. But here in alternating current circuits, very important components are not just the resistors, even capacitors, inductors. Last lesson, electromagnetic induction. We have seen a coil, it's called as inductor. Coil having high value of self-inductance is called as inductor. When inductors are also used here in these circuits. So Ohm's law cannot be applied to them in all such complicated components if they are considered in a circuit. So Ohm's law is a very simple law, mainly applicable for resistor. So resistors means a conductor. So conductors obey Ohm's law. Only in such simple cases only Ohm's law can be applied. So by using Ohm's law we got this. But in other circuits, like in this lesson, using other components apart from resistors, not just resistors, even other components which have to be used here, Ohm's law is not sufficient. So we have to use another very powerful law which you already have seen, the Kirchhoff's voltage law and Kirchhoff's current law, the two Kirchhoff's laws, first law and second law, or current law and the voltage law. So using this Kirchhoff's voltage law, we can get back the same result. So the advantage is we'll be just seeing how easily the Kirchhoff voltage law can be applied in an alternating current circuit. The same technique is actually followed even in the other circuits, that is in containing other components also. So that's the main thing here. So that method we'll be seeing here. The same method will be actually carried for even complicated components also, where Ohm's law really can't be applied. So for that reason, this topic is very useful for the sake of understanding of how the Kirchhoff's voltage law or current law and also the current law to some extent how they are applied in AC circuit. So now again coming back here. So now the important thing is when a battery or any source of current is actually sending current in a circuit, current flows in the circuit mainly because of the electric field established by the source. Just look back, come back here. So the battery, just observe the cursor here. This is the positive terminal, this is the negative terminal. So positive terminal is like a positive charge conductor. Negative terminal is like a negative charge conductor. It's just like, so take a positive charge conductor and a negative charge conductor. Now if a wire is connected from the positive conductor to the negative conductor, immediately what happens is electric field near a positive charge will be directed away from it. So electric field will be actually really created directed away from it, and electric field near a negative charge will be towards it. So an electric field is established in the wire, connecting wire, joining the positive conductor to the negative conductor. The same thing happens here. So in this external conductor, external circuit or external wire connected to the terminals of the battery, an electric field is actually created. Because of that electric field, what happens is charges begin to flow. That means electric current begins to flow. That's the important thing. Now always in electric field, a very important thing is Kirchhoff's voltage law is applicable, especially in an electric field present inside a closed circuit. According to Kirchhoff's voltage law is directly based on the conservative field property of, that is the conservative nature of an electric field. Now electric field is said to be is called as a conservative field because the reason for this is the work done is actually depends only on the initial and final position. It depends, but it's independent of the path taken. Based on this only conservative nature of the electric field, we have seen that the Kirchhoff's voltage law is actually derived. Just check the definite derivation of the Kirchhoff's voltage law. Directly it comes from the conservative nature of the electric field. Now what does the Kirchhoff's voltage law state? The statement is very simple. Supposing you are going around a circuit completely once. For example, you are starting. Now we'll take the simplest circuit here. The same circuit. Actually here again labeling of the circuit is not possible because the diagram is too small. So I'll just the present topic diagram. So let the circuit be named as something like this: A, B, C, D, A. So in this circuit A, B, C, D, A closed circuit, Kirchhoff's voltage law is applicable for such a closed circuit. In such a closed circuit, when a conservative field or electric field is present, so based on the conservative nature of the electric field, voltage law is actually derived. The voltage law simply states that the algebraic sum of all the changes in potential, change in potential is called potential difference also. The algebraic sum of all the potential differences in a complete traversal of a closed circuit will be 0. That means as we are moving from point A, going around the circuit and again coming back to A, so on the way we'll be going through different changes in potential. For example, when we are going through a resistor, there is a potential difference across the resistor. So this potential difference across the resistor is denoted by symbol V. I'll just move the I and V symbols here away from the circuit diagram, so they'll not be disturbing the derivation. I'll just put them here. So whatever things we are seeing here are simple, so nowhere any complication is there. So across the resistor there is a potential difference. So as we are going from one terminal, say one end of the resistor to the other end, from left end to the other end, right end, say there is a change in potential. Always in electric field, we have seen in the direction of the electric field potentials will decrease. That way we'll be encountering a change in potential throughout this electric field. Wherever especially components are present like a resistor or a capacitor or an inductor or even a EMF. So whatever changes in potential that are encountered, the algebraic sum of change in potential is called as what? Potential difference. Whatever potential difference that are encountered in the complete traversal of a circuit, this algebraic sum of all the potential differences will be 0 from Kirchhoff's voltage law. So applying that law, Kirchhoff's voltage law, very easily in just one step or two step, we'll be getting the same result as we got using Ohm's law. Then why both are giving the same result? The reason is this is the real relation between them. Whatever method we use, we'll have to get if the method is correct, we'll be getting the correct relation. This we got using Ohm's law, and the same thing we'll be getting even using Kirchhoff's laws. And another simple thing is Ohm's law is directly based on the law of conservation of energy. Even Kirchhoff's voltage law also, it is derived from the conservative nature of an electric field, but using the law of conservation of energy only. Especially the concept of potential energy is used here. So both are based directly on the law of conservation of energy. So both will give the same result. That's another very powerful reason why we are getting the same result, whether we are using Ohm's law or here in this particular topic using Kirchhoff's voltage law. So now we are using the Kirchhoff's voltage law applied to which circuit? Applied to the circuit AB, closed circuit ABCDA. Closed means we are starting at one point and again reaching back the same point. That way one complete loop we are completing. So applying the Kirchhoff voltage law for the loop ABCDA. Actually, whenever Kirchhoff voltage law is applied, the direction of in which we are traveling around the circuit is actually shown by means of such an arrow like this. But that is not required here because we are just labeling the circuit clearly, and the direction in which we are going also is clearly seen in can be seen in the label itself, naming of the circuit itself. So again, that can need not be drawn. The direction of the traversal means traveling along the circuit is need not be drawn here because too many things indicated in the diagram means diagram becomes congested. Already too many things are there here, so that need not be shown here. So now applying the law. So firstly, we are going from point A to B, next to C, next to D, next to A. Now what are the changes in potentials encountered as we are going along the circuit? So firstly we are going from A to B. So when we are going from A to B, we are actually going from the negative terminal of the cell, that is voltage source, to the positive terminal. So whenever you are going from the negative terminal to the positive terminal, so of any voltage source like a battery, so the potential difference is nothing but difference of potentials of the negative terminal and the positive terminal. Now from the definition of EMF, we have seen that the difference of potentials between the negative and positive terminal of a voltage source is nothing but the EMF itself. This, where we have seen this exact proof, we have seen this in the functioning of a cell, and the definition of EMF we have seen. Applying both of them, we got this result. So the potential difference encountered as we go from one terminal to other terminal, or the difference of potentials between the negative and positive terminals, is nothing but the EMF itself. So here also, as we are going from right terminal to the left terminal, that means point A to point B, the change in potential encountered is nothing but the difference of potential is nothing but the EMF. So what is the EMF here? Just see here, it's nothing but EMF. But what is the change in potential? Final minus initial potential. We are going initially from A to D. So initially we are at A means we are at the negative potential. Finally we are at D. So the change in potential is final minus initial. Final is higher. Higher minus lower is positive. So it is plus E. That's the first change in potential encountered as we are going through the across the first arm. There are four arms of the circuit. That means this is a rectangular circuit, so four sides are there. First we are going across the first side, so there is no doubt, everything is very simple. Any doubt is there, just think of it a little, very easily it can be understood. But before that, any doubt is there, just keep it aside for a moment. Next we'll go across this part. So once the entire circuit traveling of the circuit is completed, then just think of it again, whatever doubt you have, then very clearly each and every point can be understood. So next we are going across the second arm. Now across the second arm, definitely there is an electric field here, but the thing is here, this is a connecting wire. The important thing about a connecting wire is it's of zero resistance. Its resistance is practically zero. So resistance is zero, current is there definitely. That means current into resistance, potential difference is what? Current into resistance. Resistance being zero, potential difference will be zero. So change in potential between B and C will be what? There is a change in potential means potential difference. So potential difference or change in potential will be simply zero here. From directly from Ohm's law we are getting this. So still any doubt is there, just keep it aside for a moment. Doubts you are getting means you are thinking. That's a very good sign. Getting doubt is a very good sign. The reason is you are thinking, because you are there is some doubt in this means you are seeing that it is not agreeing with what or with some point which you already learned. That reason, for that reason only will get a doubt. So for that you have to think and try to find out the reason. then we'll be getting, if that definitely whatever thing is definitely right means we'll be getting the actual cause. There is some law on based on which this is actually happening here. Based on that, so we'll be getting that one. Once that is understood, how it is actually explained with a particular law. Here, what law is here? Ohm's law is helping us to find out, to know that the potential difference across this BC part is 0. The reason is resistance is 0. That way it can be still even deeper. You are thinking one more reason will be coming. Still deeper, still deeper, still deeper. So any doubt is there means there is some reason for that doubt. That reason, once it is understood, that doubt will be cleared. So try to find out that reason. So if it's, try to think as much as possible, but not too much time you should not be spending. So you should be postponing it actually, because if you go on asking doubts during the class, the lesson will be actually completed, but you will not be listening to the other portions of the lesson. Only in the first portion you will be asking the doubts. That should not be happening. Only for a short time you should be thinking, and then just remember that you got the doubt. You should have to tick that. You have to just mark it in the mind itself, because even marking on the book also time will not be there in the classroom. So mark it in the mind, and then later after the class you come back to that and find out the reason. Still you are not, still any doubt is there, you discuss it, still discuss with your friends, still not cleared, it's not, doubt is not cleared, then you ask your faculty. So that way somehow or the other you have to find out the, you have to clarify, you have to clear your doubt. Always, which is the best teacher? Only fundamental laws, the definitions, scientific definitions, the fundamental laws, or at least the laws of that lesson, they'll be the best teachers. Using them only a topic is understood, then only it is properly understood. So whatever things we are seeing here are simple, nowhere any complication is there. So now across BC portion the potential difference is 0. Next, as we are going from C to D, the potential difference across this portion of this circuit is, the resistance of this portion of the circuit is R. So current in this is what? I. So always in a single simple single loop circuit, the strength of the current at all points will be same. This is what we have seen in current electricity. Everywhere, in every portion, in every cross section, the current is same. So though it is not, we are not just showing it here, everywhere, every portion of this simple single loop circuit, current is same. So current in the resistor is I. Actual resistance of this portion CD is R. So R does not denote just, it's actually only this portion. The entire portion resistance can be taken as R itself. The reason is this portion and this portion are connecting wires. Connecting wires, resistance is 0. This portion and this portion resistance is 0. Total resistance is what? R plus 0 is R. So current into resistance of CD portion is what? I into R is the potential difference. So next is the, so this portion potential difference is 0. So we did not mention this here directly. In this remaining portion, that CD portion, resistance is R. So potential difference is what? IR. But what is the change in potential here? Change in potential is always final minus initial. So we are going from C to D this way. So C is the initial position, D is the final position. Left end of the resistance is initial end, right end is final end. So change is what? Final right potential minus left potential. Which is higher, which is lower? Current always flows from higher to lower. So this is higher. So this is higher, like positive terminal. It is like higher potential is always taken as positive potential, and this negative potential. Change will be just here final negative, lower minus higher. This is final. Just here cursor. So final is lower potential. Initial is this one, higher potential. So change in potential is final minus initial. It is lower minus higher, it is negative. So change in potential or potential difference is negative here, minus IR. Next again DA portion is what? Potential difference is 0, because here resistance of the AD portion is 0. So we have come back to point A. So the algebraic sum of all the changes in potential is what? Plus C minus IR. So what does Kirchhoff's voltage law state? Simply it states that, just see here. So whatever things we are seeing here are simple, nowhere any complication is there. So just observe here. Kirchhoff's voltage law is very simple. It always states that the algebraic sum of all the changes in potential in a closed circuit is what? It's called as sum of all the potentials is 0. So based on that, left hand side, sum of all the potentials, only two changes in potential or two potential differences are there. One is EMF and the other is resistor potential difference. So the algebraic sum is left hand side we got, that is equal to 0. So whatever things we are seeing here are simple, nowhere any complication is there. So this is another very powerful result. Though it is very simple, it's actually very important. So this is how this first equation is anyhow belonging to the previous lesson. There is not much problem. And next second result here is belongs to this particular result. It's nothing but direct application of the Kirchhoff's voltage law. This is very important result, has to be by hearted. Now this is a very important result. We got this just from a simple assumption. We assume that current is flowing clockwise, but it flows. We already know from the definition of alternating current. Current flows clockwise only for a short time interval. That means this left and right terminals are really positive and negative only for a short time interval. But in the next time interval, what happens? Current direction will be changing. In that case, will this equation be applicable? Answer is yes. In the other case also, now take the direction of current to be now anti-clockwise. That means here arrow should be downwards. Then current is flowing anti-clockwise. This will be positive, this will be negative. Then what happens is again apply Kirchhoff's voltage for the same loop. Then what happens is here in place of plus C will get minus C. In place of minus IR will get plus IR. That's also same thing, this equation only. The reason is if we multiply this equation with minus 1, we'll get that other equation, second time interval equation. That way this equation is applicable at any instant of time, whether it's current positive or current negative, doesn't matter, clockwise or anti-clockwise. Every instant this equation is applicable. So this is the greatness of the Kirchhoff's voltage law. It can be applied as it is even for an alternating current circuit. Same equation is applicable at each and every instant for an alternating current source applied across a resistor. So that's the power of the Kirchhoff's voltage law. Very powerful law. Very powerful law. So now based on this equation, almost immediately in the next step itself, we'll be getting the result. Almost within no time, we'll be getting the result. But here, some symbols will be slightly new symbols will be seeing, new ways of representing whatever things already we have seen in the AC generator. There are new symbols to be used here. Those things are actually will be very important in this particular remaining part of this topic. So the main part of the equation already we got. This is the equation, very powerful equation.